Okay, so what we're going to do today is I'll talk briefly about transformations and dilations, and I'm going to go over these notes so you have an idea as to how to do the problems. So hopefully that will work out. And I apologize for it not being set up for you today. You'll also have access to it in the classroom. So I'll start off here. We're going to talk about transformations, and what I like about, let me see full screen. What I like about transformations is that it talks about the shapes. And dismiss that, okay. The position the figure is in. So for example, I'm on a coordinate plane, and my transformation could either slide, it could reflect, it could rotate, or it could get bigger or smaller. So the idea of a transformation is going to transform the figure, like Transformers. Not quite the same, but imagine as long as it's the same shape. So if we have our basic shape, three of them deal with our basic shapes. The translations, the reflections, and the rotations deal with the position of the shape. When I talk about dilation, the size changes. So with the translation, this is important to write down on your notes. So I'll write it down on the paper here, on the thing. When I'm dealing with the translation, hopefully this will work, the orientation stays where it's at. Stays. It doesn't move at all. So for example, if I'm taking a look at this particular picture here, with this orientation here, you'll notice this is always pointing up. No matter what happens, it's pointing up. In a face-to-face classroom, I take my hand and I slide my hand. I'll show you like this. I take my hand, and then my hand is always pointing up. My fingers are always pointing up. Okay. Now, if I'm a reflection, my hand's going to flip. It's going to go like that, here to here. It's a reflection, okay? It's like the same thing, a butterfly. Same thing, okay? Rotation, it's obviously going to rotate. So, if I look at this reflection here, look at this reflection guy over here. Here he rotates, he flips over. If I rotate him, I'm on an axis. I'm on a point here, and it's going to turn round and round and round. It could go clockwise, it could go counterclockwise, okay? Now, dilation is about size. Well, here's my little Tigger. Tigger is one size right here, right? Well, Tigger got bigger over here. So it's going to blow up. If I blow up a balloon, that's a dilation. It's a certain shape of my Tigger here. He gets even fatter. He goes over here. There's always a point. This is a very artistic thing. You can look at the point of I think it's a perspective point. I think it's called. I could be wrong. Probably am wrong. But it goes along those lines where no matter what happens, it's the same exact shape. It just got ginormous. Or if I started off ginormous, it got smaller. They call that the scale factor. What's the scale factor with our shapes? So a couple of things, little tidbits. Let me switch to this guy here. You go away. And if I'm looking over this here, transformations, the orientation never changes. Very important to note that the orientation never changes. Now, when I deal with reflections, it's actual, and I'll show you my card. I actually have a card. Hope I could find it. With all, I call it my cheat sheet card, my transformation cheat sheets. And I've kept it over the years, and it has all these little things on there. And I know that when you get to the high school, they'll let you keep a little cheat sheet too. But it has all the rules for transformation. You can just look up Google transformation rules, it'll show you what it means. Essentially, if I reflect over the x-axis, so if I take my transformation and reflect it over the x-axis, go in this direction, folding it over. This is not over, this is over the y over here. So going over the x-axis, that means if I have my regular ordered pair, x, y, when I reflect it, that means my new ordered pair will be x and the opposite of what the previous y was. So if it was 3, 4, it'll be 3, negative 4. If I rotate it over the y-axis, keep the y sign, but I want the opposite x sign. So if it was x, y, now it's going to be the opposite. If I was at 5, 7, it's now going to be negative 5, positive 7. Same y's. Now, when I rotate, it's all a little bit different with rotation. Here are, they call these things a rule. So if this is called a rule, here's one rule here, x, y, then it goes to x, comma, opposite of y. Here's my rule for reflecting over the y-axis. Again, I would not expect you to memorize these things ever. I give you guys a cheat sheet because it's dumb to memorize them. But you have to understand the concept of what happens to my ordered pairs. If I take a rotation, now rotation is going to be a little bit different because rotations mean I'm going to take my figure and rotate it around some point. Now here, I can rotate, I can flip it over the x or y axis. I can also flip it over a line. X equals 2, I can flip it over that line here. when I rotate, the same thing happens. I can rotate it on one point. If you think about a top, the figure is exactly preserved. If I spin a top, those little kid spinners, the top is exactly preserved. It rotates it around. No different here, except for I'm rotating it on the origin. I'll say that I'm rotating on the origin. So when I'm going to rotate around the origin, this is what happens with my signs. 180-degree rotate, opposite of x, opposite of y. 90 degrees clockwise, that means I'm going this way clockwise only through one quadrant, right? It's 90 degrees, one turn, one click, click, click. No, I'll show you more about that when we see each other in class. And 90 degree counterclockwise, it goes the other direction. Now, dilations, and again, here are your rules for that. Sorry about that. Dilations can also be from one point or from the origin. So look at my dilation. Here's a dilation from one point here. And I talked about that scale factor earlier. So if I say I'm going to get 5 times larger, whatever my ordered pairs are, say I have 1, 1, it's an ordered pair, I just multiply that by 5. So my new ordered pair is 5, 5. So just because everything gets multiplied 5 times larger. Now that is a, if you think of it this way, there's a scale factor greater than 1, it's 5 or bigger, 1 or bigger, it's obviously 5, 5 is bigger in that case. Then they call that an enlargement or a stretch. If the scale factor is smaller, between 0 and 1, then it's a reduction. Now, obviously, if the scale factor is 1, then it's this congruent figure. So, we either have a stretch, which makes it bigger, a reduction, which shrinks it, or it's the same, okay, which is congruent. And why would you have a scale factor? Why would you dilate it? Because nothing happened. So, that is what we're dealing with the dilations. I have a couple links that you can click on here. We're going to do this in class, this messing with Lisa, so don't do that now unless you want to, but give us something to do in class, okay, guys? I took some of these notes from MathBits notebook, and I found some so good lesson, okay? So let's go ahead and do a problem together. This is why I want to do the patty wax paper. Okay. Here are some of the problems that we're going to do, and let's just go ahead and let's do... not the dilations. Let's start with the transformation first. Translation first. And okay, let me find a good one to do. Ooh, I have some over here. Let's go to the back page. Let's go to the back page first. Okay. That's a dilation. Let's do 31. Okay. So it's always helpful to know what the ordered pairs are. Okay. So let's go ahead and write down the ordered pairs. I'll press pause and you guys will know the ordered pairs. Okay, so now I went ahead and filled in all these ordered pairs. Well, I'm starting to see a pattern first of all. Here, the signs are just switched. This is kind of a pattern. So we wanted to determine what exactly happened. So just that you guys know, this is my original. My original is, they call this the pre-image. Okay, this is the pre-image. And then, I believe, sure how the software. Then we have primes are the new image. So M prime, N prime, K prime, L prime. So something happened. Something happened to this particular transformation. We want to figure out what it was. That all of a sudden I went from here, this is my original image, to here, my new image. Here's my original. Here's my. So I want you to do this. Do me this favor. Take your graph, and I want you to trace it. Use your patty paper, the graph paper, and I want you to trace it. Put your axes on there. Always have your axes and always label y and x's. When we start moving things around, you could get really lost. Okay, I'll wait for you guys. Press pause. Okay, so now, here's your graph. I want you to rotate it or flip it, or what can I do? How am I going to get this guy to match right on top of that guy? Well, here's how we do this. You keep your pencil down, and I'll rotate it once. Oh, it's not matching it. Rotate it twice. Is that matching it? Are they right on top? You put your L's on L, K is on K, N's on N, M's on M. Yes. That matches it exactly. So this was a rotation. I went counterclockwise. Actually, I went clockwise, because this is how the clock goes, right? I'm like this. And I went one click, because I went with my axes, one click, and one more quadrant turns, the second click. And I landed right on top of there. So really, I just went over there twice, okay? So this is a counterclockwise rotation. Counterclockwise, and rotate twice. Okay, this is totally not how you're supposed to write it. This is the basis of how I want you to write it for the startup. Just a brief description. I did it counterclockwise. Now you might say I did it the other way. Let's see if I could go clockwise. Clockwise. Sorry. We did clockwise. Sorry. I started off here, and I went with the clock. 1, 2. Now let's see if I go without the clock. Will it still work? If I go against the clock. 1, 2. Does that work? Yes, that works too. Okay. So I went 90 degrees and 90 degrees. How many? Oh, I'm going to show you guys this. It was actually a counter. If I do a counterclockwise or a clockwise rotation twice, that's a 180 degree clockwise or counterclockwise turn. Rotation. So I rotated 180 degrees. Now here's where it's kind of interesting. Hopefully this works out mathematically. It doesn't really matter if it's clockwise or counterclockwise. If I'm looking at my rule, what's my rule? My rule for 180 degrees rotations about the origin is opposite x, opposite y. So let's see if it worked out. Is this here's m is 4, -2, but the new one is going to be opposite x, opposite y. So the rule is opposite x, opposite y. Let's just see if that's true. Is my x, it's opposite. That's opposite. It is true. Let's look at n. 2 and -2, -4, 4. Those are opposite as well. Well, 0 doesn't make a difference, right? But the opposite, yes. Here I have 0, 0. Opposite, yes. So that's my rule. So I have 180 degrees clockwise, or counterclockwise, it doesn't matter, rotation about the origin. Okay? And so I want you to do, for homework, just do this. Let's see. Just describe, if you can, and again, it doesn't have to be great, putting your ordered pairs to the back page. Do the ordered pairs, like I did here, for the back page. Label the back page. Okay? And then describe in words what you did. So you'll have to trace over them, okay, on your patty paper. And again, you should be able to get 6 graphs on your patty paper. It might be kind of tight. But trace over those graphs and then figure out what you had to do. Now for dilation, obviously you don't have to do that. This is obviously dilation because this one went from bigger to smaller. But I want you guys to figure out what happened from this guy to this guy for all of them, and then try and see what you could do. Are they reflections? Are they rotations? What could it possibly be? Give it your best go, and then we'll talk about it on when I see you next. Okay, again, just do these problems here on this page. Okay, talk to you later.